Morning, everyone. It's good to be here in Detroit talking about automotive Ethernet. The slides are not advancing. So before I get started, I'd like to go over a couple of fundamental concepts that I'll be referring to in this presentation. Stand by. This could be a long presentation. Thank you. So first, a next hop is simply the next bridge, router, or endpoint to which a packet must be forwarded. It is the job of any forwarding system to transmit a packet to its next hop. Tunnels are used to convey one or more packets as the payload of another packet. Tunneling is not an esoteric concept. Tunnels are essential. For example, UDP is tunneled over IP, and IP is in turn tunneled over Ethernet. Okay, now that those fundamentals are out of the way, let's dive on in. Still have problems here. There it goes. So we in this room share a common set of objectives in the advancement and improvement of automotive Ethernet networks. In particular, we want to maximize networking efficiency by increasing performance while reducing cost. We want to simplify the networks while enhancing their flexibility. And we want to increase availability through improved security and resilience. We face a number of significant challenges in working towards these objectives, of course. I think we can all agree that replacing a complex set of legacy automotive networks with a unified Ethernet backbone will go a long way towards achieving these objectives. But there's one particular challenge that is proving somewhat intractable, and that challenge is the topic of this conversation. In particular, there are hundreds of sensors and servos that make modern and future cars safer, more efficient, and more enjoyable to drive. Communication with these sensors and servos present a significant burden to the compute and networking resources of a car. Briefly, a sensor is any function that measures some aspect of its environment and reports that measurement to an ECU as an input. Servos, by contrast, act upon the environment based on output commands from an ECU. Sensors and servos come in a huge variety. Communication with both sensors and servos presents significant CPU processing overhead. Sensors are particularly burdensome due in no small part to sensors generally outnumbering servos. In the category of high data rate sensors, the very obvious example of video cameras, other spatial sensors such as radar and LiDAR also fall into this category. Medium data rate sensors measure the real-time condition and state of a multitude of systems and functions. And low data rate sensors include things like buttons and switches, which have data rates that are essentially DC. But the high data rate sensors are particularly, they may seem like they're the most burdensome in a network, but though their data rate is very high, their frame rate is actually rather low. For example, if we have a car with 12 cameras, each transmitting at 60 frames per second, that's only 720 interrupts per second generated at a centralized ECU. And if these cameras are properly synchronized, which they should be, then it's only 60 interrupts per second at a central ECU. It's the medium data rate sensors that are particularly burdensome. For example, if a car has 100 such sensors, each transmitting 100 times per second, just to keep the math simple, it's roughly 10,000 frames per second. Or put another way, that's an interrupt every 100 microseconds. And this will burden even the most powerful of CPUs. I am reminded of the age-old question as to whether it would be more difficult to fight one horse-sized duck or 100 duck-sized horses. And these small, medium data rate frames are the duck-sized horses and could be rather formidable due to their sheer numbers. So briefly, let's go over the contributions to this overhead. The interrupt signal is simply the first step in a long sequence of events. The delay between the assertion of the interrupt signal and the CPU actually reacting to that assertion is interrupt latency, which can be highly variable, but it does not directly contribute to overhead because the CPU is ostensibly doing productive work during this interval. The current processing context must be saved by the CPU when it reacts to an interrupt, and that context must be restored at the end of interrupt processing so that it can pick up where it left off. The exact cause of the interrupt must be determined, and in complex systems with many interrupt sources, this can be a lengthy process. Typically, it's beneficial for a CPU to exit the kernel mode as quickly as possible, and that means any extensive work required by an interrupt is usually pushed onto some kind of a work queue that's maintained by software. Physical event work and completion queues must be queried by the software to determine the state of the hardware, and these queues must be updated as a consequence of interrupt processing. And finally, every received frame must be examined to determine which of potentially many handling functions that frame must be dispatched to. So how do we address this overhead? Now, the first and most obvious thing to do is interrupt coalescing. Interrupt coalescing attempts to share a single interrupt across multiple received frames. One approach is to disable further interrupts upon receiving the first one. The software can then detect additional received frames through polling and looping, and when the software determines there's no more work to be done, the interrupts are re-enabled. And speaking as a hardware guy, the beautiful thing about interrupt coalescing, it's almost entirely a software solution. So getting back to this list, interrupt coalescing addresses a number of these factors, but not all of them. Software must still manage the queues and must still dispatch the frames to functions. So the next thing to consider is frame coalescing. But put simply, frame coalescing attempts to combine multiple frames into one. It does this by delaying the transmission of these short frames and then organizing them into groups based on their next hop. If frames share a common next hop, they get lumped into the same group. This group of frames is then encapsulated into the payload of an Ethernet frame. And then one of the benefits of this frame coalescing is because we're reducing the number of frames, we're also reducing the number of interrupts, so it becomes a first-order approximation of interrupt coalescing. However, it's reasonable to combine these benefits. This drawing shows how a series of CAN frames may be packed into the payload of an Ethernet frame. A single AVTP header introduces a collection of CAN frames, and then each CAN frame has its own ACF header. A comparable encapsulation is available for some IP. Unfortunately, there are almost as many ACF header variants as there are CAN header variants, and this makes processing in hardware a little tricky. If we consider CAN frames with 8-byte payloads and the 8-byte ACF header, then we see on-the-wire bandwidth savings of between 0 and 80%, depending on the number of CAN frames packed into each Ethernet frame. Now, given the relatively low data rates of CAN and CAN-FD, these bandwidth savings are probably meaningless when transmitting across a multi-gigabit Ethernet link. However, this could be substantial and worthwhile when transmitting across 100 megabit links. So getting back to this list, by coalescing these frames, we've reduced the amount of queue processing that's required. But how do we attack that last problem? After all, if we receive an Ethernet frame that's filled with CAN frames, we still have to examine each and every CAN frame to determine which function is intended to handle it. And the answer to that is what I call functional coalescing. Functional coalescing combines the benefits and behaviors of frame coalescing with an awareness of the purpose of each of these small frames. A frame's purpose is expressed by the identity of the function that is intended to handle that frame. And functions can be identified by, for example, examining the identifier field of a CAN header. So what we're doing is we're packing and organizing these CAN frames into the payload of Ethernet frames such that all of those CAN frames share a common handling function. This reduces or eliminates the dispatch overhead. So let's bring us all together and work through an example. This diagram shows a network where we have 6 CAN sensors that must deliver their frames to 6 corresponding software processes. The origin and forwarding nodes will organize and group these CAN frames according to their next hops. So origin endpoint 1 has 2 transmit ports and will organize its CAN frames accordingly. Origin endpoint 2 has just 1 transmit port, so all of the CAN frames end up in a single Ethernet frame. Now the red and green frame is enqueued in forwarding node 1 without modification because it has just 1 possible next hop. But forwarding node 2 must unpack and repack those CAN frames into new Ethernet frames in order to optimize them according to their next hop at this point in the network. Now when we get to the destination nodes, we are going to again unpack and repack those CAN frames, this time organizing the CAN frames according to their targeted software processes. So here's a recap of the behaviors we just saw. So the origin and forwarding nodes organize the CAN frames according to their next hop. This improves network utilization by reducing the frame count and improving the payload to header ratio. When we get to the destination node, we are now organizing the CAN frames based on their intended software processes. This reduces CPU overhead. Overall, this process is somewhat analogous to that of a railroad switching yard, where freight cars are split from incoming trains in order to build new outgoing trains. This diagram shows the processing steps that are required to perform the next hop and functional coalescing that I've described. The pipeline consists of an alternating series of forwarding and coalescing functions. The frame coalescing functions operate as you might expect. Frame headers are examined and forwarding decisions are made. The demultiplexer then carries out those forwarding decisions. The coalescing function both coalesces and decoalesces. This means that this function can pack CAN frames into the payload of an Ethernet frame. It can also unpack those CAN frames from an Ethernet frame and present them as a separate individual CAN frames. So at the origin end of the network, where we are receiving CAN frames from a bunch of sensors, these CAN frames are forwarded to a coalescing function, which then builds an Ethernet frame. The Ethernet frame is then forwarded to an Ethernet port for transmission into the network. In the middle of a network, we're receiving Ethernet frames filled with CAN frames, and we want to now reorganize those CAN frames to optimize them for the next hop. So here you can see the Ethernet frame is forwarded to a coalescing function that breaks apart the Ethernet frame into a series of individual CAN frames. These individual CAN frames are then forwarded to a new coalescing function that organizes them into new Ethernet frames, combining them with CAN frames received from other frames elsewhere, and either at the same time or slightly different times. And the resulting repacked Ethernet frames are then transmitted via Ethernet. And finally, when we get to the destination endpoint, we're following roughly the same path, but this time the second coalescing function is organizing the CAN frames according to the targeted software process, and the resulting Ethernet frames are delivered to host CPU for processing. Alternatively, it's possible to take a receive frame filled with these CAN frames, break them apart, and then forward them and transmit them via their native CAN ports. If we roll up that pipeline that I've been showing, we end up with something that's actually rather simple. And here are those scenarios overlaid on top of one another. Now that may look like a lot of looping and passes through the frame coalescing and forwarding functions, but again, we have to bear in mind the relatively low data rates of CAN and CAN-FD. Even with all this looping through these functions, this represents roughly a single-digit percentage of a multi-gigabit system's total capacity. I've been talking a lot about receive frame processing and its overhead, but now what about transmit? Transmit overhead is somewhat lower than it is for receive, but it is still meaningful, still significant. And the way to attack that is to perform frame coalescing at the origin as well. And what this means is that a software process in an ECU that needs to transmit a bunch of CAN frames to some servos or actuators scattered about a car can concatenate those CAN frames into the payload of an Ethernet frame and then deliver that to the networking hardware as a single object. This means there's only one set of queue operations that are required to deliver that Ethernet frame to the hardware. The networking hardware can then break apart that payload and recombine it with other Ethernet frames that were delivered at the same time and organize those CAN frames according to their immediate next hops. And then, of course, at the far end of the network, these CAN frames are broken out of their Ethernet payloads and are transmitted via their native CAN ports. But there's one more thing that must be considered. We can't ignore 10-base T1S. When our hoped-for all Ethernet future arrives, everything I've said related to CAN frames applies equally well to 10-base T1S. Entire Ethernet frames, or preferably just their truncated payloads, can be concatenated together and transported via an Ethernet tunnel. So in conclusion, I'd like to share a couple of closing thoughts. Dealing with all of these small frames is a real issue. My software colleagues remind me of this on a regular basis. Interrupt and frame coalescing are good first steps, but there's more that can and should be done. Next-hop coalescing at the origin or midpoint has benefits in reducing networking overhead. But importantly, functional coalescing has significant benefits in reducing software overhead at both the source and the destination. And of course, all of this work must be done 100% in hardware with zero software intervention. After all, that's kind of the whole point of offloading work from the CPUs. With that, I thank you, and I'm happy to take any questions you may have.
Great, thank you, and open it up to questions for Brian.
Saying that you're going to be doing all this in hardware, I presume, depending on the CAN types and messages, you need the ability to configure the hardware. Is that how you intend to sort of work through the actual different size of CAN packets and how you're going to coalesce and decoalesce the actual messages?
Yes, without revealing anything that's proprietary at the moment. Yeah, we do have hardware that can interpret the various CAN header formats and understand the various ACF header formats and can map between them, plus additional formats that are handy and useful within our system. And again, it's all done in hardware as, as fast as you want to go. There's no real upper limit. We can occupy 10, 15, 20% of our total system with this kind of processing without imposing any kind of a burden.
Okay, thank you.
Thank you. Other questions? Yes.
How do you envision the coalescing on the 10-base T1S? Would it be like the coordinator taking in the packets and when it's ready, it'll just send them out when it wants?
That's one approach. I'm leaving the software-related problems to software experts. That's not my field. My colleague Anil is more qualified to address that. But yes, whichever function wants to send multiple messages to a variety of destinations can aggregate those messages, either 10-base T1S frames that it's received or CAN frames that it's received, or more specifically, if you're trying to talk to an actuator, if you want to send these small messages, you can aggregate them into an Ethernet payload, and then the networking hardware at the various stages of origination and forwarding and termination can reorganize those payloads as needed. And that's really the secret sauce there. It's the ability to break apart and reassemble flexibly. Because if you only do your organization of these small frames at the origin, you have to take sort of a lowest common denominator, sort of approach, and saying, well, these frames are all intended to follow the same path throughout the network, and you may not be operating optimally at every hop. And certainly organizing them by the path and by the software process reduces the number of things you can pack into one Ethernet frame without waiting unduly long to fill up a frame. And that's one of the things you have to be careful of, is you don't want to use this packing process as accidentally increasing the latency dramatically. So you have to be careful in how you adjust your parameters.
Yep. Thank you.
Okay, thank you. Any other questions? Well, hearing none, thank you very much.